Today we're going to take a look at inverse functions and how they work and why we have them, and kind of looking at what is an inverse function, how do we prove that two functions are inverses. But first, in order to do that, we need to define what an inverse is. So an inverse of a relation is just a set of information. Sometimes that set of information is just a set of points. Sometimes that set of information is a graph. Sometimes it's an equation. So just a relation is just a set of information. So what is the inverse of a relation? Well, the inverse of a relation is a different relation that reverses another relation. So basically it's taking information and reversing them. So every x that you see in an inverse, it becomes the y. And every y value that you have when looking through the lens of an inverse becomes the x. So see, essentially it's the reverse of the two. So in order to denote that something is an inverse function, you take whatever you have labeled it. In this case, we labeled it r. So we have the notation r to the -1. Now, a lot of people assume that's an exponent of a -1, but it is not. Usually you'll see it in the notation that includes the x value. It is not a negative exponent. Please do not refer to it as like x to the -1 exponent. We can talk about it in casual conversation as like r to the -1 or r -1, but please understand that that is not an exponent of a -1. It's just a notation format, because you have to include your variable piece with it as well. It's not a standalone. Okay, so if I have this function r here, I'm going to try to do my original functions today in blue and look at inverses in red, so we have these color coordinated functions. If I have my original function r, what I'm looking at is the inverse of r, or the reversed version of r. So if I had 0, -7, and I reversed it, it'd become -7, 0. That 7 looks weird. There we go. If I had -1, 2, and I reversed them, it would become 2, -1, and so on. -2, -4, 3, and 6. So it's essentially taking your x, y values and switching them. We can switch those ordered pairs and you get the inverses that we see here. So again, a relation is just a set of information. So if you were given a set of ordered pairs, switching the x and y. When we do that, we have this concept called one-to-one. One-to-one means that for every one x value or one input value, there is a unique and different y value. And so the formal definition states that a function and the inverse, or and its inverse, because it's going to be paired together, are considered one-to-one so I'm just going to kind of shorthand it one-to-one if both are functions, or they pass that vertical line test. So we studied early on that in order for something to be a function, it's got to pass a vertical line test, meaning that as I move a vertical line across my graph, it only touches once. Well, if we're looking at inverses, and inverses are being reversed, the reversed or opposite of vertical is horizontal. So instead of moving my, line from left to right, we're moving it up and down. So a horizontal line test is used to determine whether a relation is a function or if its inverse is a function. The horizontal line test is used to determine not just f, because that's what we use for the vertical line test is the original. So vertical line test works for f, but horizontal line test works for the inverse of f. So f negative 1 of x. In order for something to be one-to-one, it must pass both. So if we look at these examples, example number 1, if I look at, and it's kind of hard to see on the printed version, but here's that function. It's a linear function. If I could trace. Okay, here's my linear function. If I look through the lens of a vertical line test, it only intersects at any point once. So I know that my linear function is a function. The question is the inverse also a function? So instead of working vertically, we look horizontally. It's only ever intersecting once. So we say, hey, not only does it pass the vertical line test, it also passes the horizontal line test, meaning that this is one-to-one, or meaning that both the function and its inverse are indeed functions. Number 2, this is actually a trig graph. It's a sine graph or sinusoidal graph. So it's got like hills and valleys, looks like waves. If we look at it through the scope of the vertical line test and just saying, hey, is my function or is this graph that I see a function? Well, vertically, it's only intersecting at any point once. So is the graph a function? Yes. However, is its inverse a function as well, or is it one-to-one? So instead of vertically, we look at horizontally. And I can stop here because at this point, I have 1, 2, 3, 4, 5, 6 intersections. So although the original graph was indeed a function, the inverse is not. And since both have to be true for it to be one-to-one, we have to say that this is not one-to-one. Number 3 is an example of a rational. I know it's irrational because the graph is split along 2 asymptotes. I have one vertical asymptote that is occurring right between those 2 green sections, and I also have a horizontal. So I know that I do have 2 asymptotes which occur in a rational function. The question is the original green graph a function? Does it pass the vertical line test? So we start looking. Too much. Here we go. It only touches once. It only touches once. It only touches once. It doesn't touch at all. That's okay. It only touches once. So is the green graph a function? Yes. Is the inverse a function? So if I ran a horizontal line test, this is good. It only touches once, only once, none, and that's okay. 1, 1. So the horizontal line test passed, the vertical line test passed. So we say, yes, this function is one-to-one. Look at, we're not going to do all of them. I'm going to kind of skip around some. Look at number 5. This is a strange one. It is a horizontal line. So I want to say, hey, is my original graph, is this original green a function? So we start looking vertically and we're saying, hey, vertically, it passes the vertical line test. Horizontally, however, it fails because the entire section is highlighted. Instead of having one intersection between red and green, the entire thing is. So we say, unfortunately, this is not, this one is not one-to-one. If we look at 6, very quickly, it's easy to tell, hey, here's my graph in green. The red does intersect more than once, so it failed the vertical line test. The graph itself is not even a function. So we say that this is also not 1-to-1. So looking at kind of diving deeper into it, inverse functions, the notation, and we've kind of studied that already, is that f to the negative 1 of x, or f negative 1 of x. Not all functions have an inverse. And we kind of saw that in those graphs. Like, it could be a function because it passes a vertical line test, but it's not. It doesn't have an inverse because, well, it fails the horizontal line test. Our job is to be able to prove them algebraically. So it's very easy to tell on a graph, because you can say, oh, it passes a vertical line test. It doesn't pass the vertical line test. It passes horizontal. It doesn't pass horizontal. But it's when you have to show it algebraically. You have to prove it. So if we look at the concept of inverse, inverse means a reversed order, or switching x and y. The same is true when we're looking at equations that represent functions and trying to find their inverse. Right now, this function can be written as y equals 4x minus 8. So swapping out the f of x with a y. The reason we do this is because, again, talking about inverses are reversed order. X's become y's and y's become x's. So when we're trying to find the inverse, we say, hey, look what happens when we switch these. So now we have, instead of y equals, we have x equals. And everywhere we once had an x, we now have a y. Perfectly fine, except that this is not written in function notation, because function notation always starts off with like a y equals. So our job is to put it back in the correct order so that my final equation is something that I could graph. So like a y equals. So if I had to try to get y by itself, we call it solving for y, I would use my order of operations. I would say, well, the first thing I need to do is add 8 to both sides. I'm still looking to get y by itself, and my last step is to divide. So what I have is x plus 8 over 4 is equal to y. In order to tell the difference between what we originally started with, originally we had an f of x. To show the relationship between these two pieces of information, all that work that you just did, we're going to take that answer and we're going to write it in inverse notation. So saying the inverse of f is x plus 8 over 4. And when you do it this way, you can see the relationship, and you've displayed it using mathematical notation. So there's no arguing that, hey, you just have this random equation. No, it's linked to f. It's the inverse of f. So we want to make sure we're using the right notation, because you don't want to, like with your friends, you don't want to refer to somebody by their wrong name or by some like nickname that you have for them in a formal setting. So in a formal setting, I would refer to all of my friends or all of my peers or all of my colleagues using their first name or their last name. I wouldn't call them what I call them when it's just the two of us together, like nicknames and things like that. So I want to be as formal as we can be. I only have a couple on this page for sake of time, but I wanted to go over like number 10. It's a strange one. A lot of people freak out because it's a fraction. So again, I'm going to swap out f of x for a y. So I'm going to rewrite it. Y is equal to 5 divided by x minus 8. So this is just a different representation of the original. So in order to start looking for the inverse, we switch that x and y value. So we have x is equal to 5 minus, or sorry, 5 divided by y over y minus 8. Now I can start solving for y. I do have a fraction. So in order to get rid of my fraction, I would multiply by my denominator. And I've kind of kept them separated so that I can divide by x. And now I have y by itself. Now the shortcut is, if you notice where x originally was and what was originally in the denominator, they've switched places. So a shortcut is to just switch them out. Oops. I'm going to do like a little switcheroo. That's a shortcut, but the real reason behind it is because you have to multiply by the denominator and then try to get that by itself. So if I'm trying to get y by itself, the last thing I have to do is add 8 to both sides. So I have 5 over x plus 8. And then to show the relationship, I just put it back in inverse notation. So the inverse of f is equal to 5 over x plus 8. So let's look at one that involves a radical. So again, kind of getting used to rewriting things. So I'm going to swap out f of x with my y is equal to the opposite of x plus 2 square rooted minus 7. So in order to start that inverse process, I'm going to switch these two. So instead of having y equals, I have x equals negative square root y plus 2 minus 7, and I start working towards getting y by itself. Order of operations, so old school foundational math says that the first step is anything added or subtracted. So I do have a radical, which means that I kind of have to leave it alone. Nothing can come in, nothing can go out until it's time to deal with that. So I'm going to start by adding 7 to both sides. So now I just have a negative sign to deal with. So I'm going to divide by negative 1. And I'm going to do a little number crunching here, so don't freak out. Negative x minus 7 is equal to the square root of y plus 2. I mean, I'm getting closer and closer to y. Now I have my radical by itself. I can deal with my radical. Well, that radical is a square root sign. So the only thing that cancels out a square root is squaring. So if I square both sides, then I cancel that square root. It makes that square root go away. So I currently have negative x minus 7 squared is equal to y plus 2. So my last step would be to move the 2 away from the y, or subtract 2. So my inverse is negative x minus 7 squared minus 2. It's a little bit longer. It's a little bit messy, but it kind of introduces that idea of a radical symbol. If I had a cube root, I would cancel it out with a cube. But most of the times you're only going to see squares and cubes. Okay. Our job in pre-cal is to not only find an inverse or find a piece of information, but it's also that communication piece that says, hey, I know you know how to find it, but can you prove it beyond a shadow of a doubt? So in order to verify something and say, hey, what I have done is legitimate. It's not just, just moving a bunch of numbers for the sake. Like, there's a legitimate reason and I can prove why. So I think about I think the best way to explain verifying inverses, y'all forgive me, okay? It's with Walmart chicken. I know, you're probably thinking, oh my gosh, my teacher's lost her mind. Yes, I have. But think about it this way. I have $5 in my pocket and I need to make dinner. So I go into Walmart and I say, what can I buy with $5? Well, I can buy a whole rotisserie cooked chicken for $5. So my input was 5. I walked in the store with $5 and I walked out of the store with a whole rotisserie chicken. Okay? Now, a couple weeks go by and I go to somebody's house and they're like, hey, come over for dinner. And I'm like, oh, yeah, sure, no problem. So I roll up at someone's house and I realize that for dinner, they have a rotisserie chicken. Oh my gosh. Well, when I see the rotisserie chicken, because I've already had the experience of going into the store and buying it, I know that, oh, they have a rotisserie chicken. Therefore, they must have had $5. So verifying something means whatever the input was for one function, an input becomes an output. If I look at something and I know the output, I just get back the input. So again, if I have $5, I can buy a chicken. If I can buy a chicken, I have $5. So we're looking at that. So verifying inverses is when you have two functions, say f and its inverse, and they are reflections of one another across the line y equals x and x equals y. So if y equals x, x must equal y. If I have $5, I can buy a chicken. If I can buy a chicken, I've got $5. That's kind of how it works. We don't focus a lot on graphing. I do want to show you one of the simpler ones in the graphing. What we're going to stress in AP Pre-Cal is the algebraic manipulation of it, proving it algebraically. So if I was to find the inverse of, let's say, 3x minus 6, and I'm going to go very quick, so if you need to, you can slow down the video, rewatch it, do what you have to. I know I've got to switch them, and then I start solving for y. All right, here we go. So y minus x is kind of this dashed, it's very free-handed, but there's your y equals x. So a reflection. If I graph my original function, it is written in y equals mx plus b, so I know it has a y-intercept of -6 and a slope of 3. So up 3 over 1, up 3 over 1, over 1, 2, 3 over 1. Very rough sketch, but this linear function is what I get. I get to choose, okay? I get to choose what points I use in order to graph. So again, I don't change things, but I know some people might see this and say, hey, isn't this the same as 1/3 x plus 2? Yes. Okay. I just started with 1 and said 1 plus 6 divided by 3, it's not pretty. 2 plus 6 divided by 3, not pretty. 3 plus 6 divided by 3, whole number, graph it. Okay. So you do you, boo, and I'm going to do me. I will go with this one. So I'm going to start at 2, and I have 1/3, so up 1 over 3, 1 over 3, up 1 over 3. Here we go. So if we look at the blue versus the red, they are reflections diagonally. So we can see that, hey, if I flip the blue one over, it's going to land on top of the red one. That's to prove it graphically. You could also just look at ordered pairs and say, hey, I've got an ordered pair here. Let's kind of zoom in a little bit. I've got an ordered pair here at 6, at 6, 4, which on the red one, which means that I should have one at 4, 6 on the blue one, and I do. So it's kind of looking at those graphically. What I want to spend the time on, though, is not looking at it graphically, but looking at it algebraically. Algebraically means that you're going to do a composition. So again, the $5 chicken. If I have $5, I can get out a chicken. If I have a chicken, that means I had $5. Both of them have to be true in order for the inverse to be proven. So they have given two functions, and they said, hey, can you please verify that these guys are inverses of one another? So in order to do that, we have to say, if I evaluate them or do like a composition, I have to check both directions. If everything checks out, then that's your verification. Again, if I have $5, I can buy a rotisserie chicken. And if I can buy a rotisserie chicken, that means I have $5. They verify each other. So I'm going to start with my f function. Let me do this in black. Zoom in so I've got some space. F of g of x. So I'm going to start with my f function. So everywhere I see an x, I'm going to put a set of parentheses. So x minus 7 over 2. And I'm going to fill those parentheses with my g of x, 2x plus 7. Okay, so in the numerator, I have 2x plus 7 minus 7. That just gives me 2x divided by 2. And if I simplify that, then f of g of x is equal to x. You want what you originally started with. Again, backwards thinking. If I have $5, I can get a chicken. If I have chicken, I have $5. So that's where that x comes in. So if you evaluate it or you compose it, you do like that composition, you do all the math, you clean it all up, and you get out an x, you're on the right track. Now the thing is, you can't just have one of them be x, both of them have to. So we do kind of backwards verification. So if I'll have f of g of x came out to x just like it's supposed to. G of f of x. So I start with the g function, and I'm going to put in the f of x. So 2x plus 7. And I'm going to substitute my x value for my f of x. So I notice that these two cancel out, leaving me x minus 7 plus 7. X minus 7 plus 7 is just x. Because both of these came out to x, that's how you verify. So let's look at some on the next page. Again, I'm not going to do all of them. I'm actually going to pick the easy ones. We never, in AP Pre-Cal, we never verify graphically, okay? It's all algebraically. So let me pick one that we can do together, maybe 6 and 7. They're not too awful. Where we not only have to find the inverse, then we have to verify it. And we're not verifying it graphically, we're verifying it algebraically. We're going to prove it. So let's look at 6. If I have to find the inverse, the first thing I'm going to do is kind of rewrite this to include my y value. Inverse means that x and y switch places. And then solve for y. So in order to get y by itself, I'm going to have to subtract 2 from both sides. And just like before, a square root was the inverse of squaring. Now a cube root is the inverse of cubing. So x minus 2 cubed is equal to your inverse. And we want to write that using that inverse notation. This is the version we love because it makes the connection between the two. It's not just something that we made up, but we're showing, hey, these are inverses of each other. Okay. So we did all the work. Now what we want to do is we want to verify. Remember, verifying means that I'm going to call my f of negative 1 g of x because we were doing composition of functions, and we were using f and g's. Okay, so I'm just going to let g of x represent that inverse, just because we had color-coded blues and reds before. So I have to check both and make sure both come out to that x value, that original x value. So my original function was the cube root of x plus 2. So everywhere there was an x, I'm going to leave a space. And I'm going to fill that space with what we determined was our inverse. So we found it, and now we have to prove it algebraically that, hey, these really truly are indeed inverses. So a cube root and a cube cancel each other out, leaving us with just x minus 2 plus 2. And if I math that, I get just plain old x, which is exactly what we want. It cannot just happen on one side. It's got to happen on both. So we're going to start with the g function. And everywhere we see an x, we're going to put in our original function. So start with that inverse. Well, we said the inverse was x minus 2 cubed. And my original function was the cube root of x plus 2. So the plus 2, the minus 2, they cancel each other out. So I've got a cube root of x cubed. The cubes and the cube roots cancel each other out, and we're left with just a x. And both sides are checking out to be the exact same x value. Therefore, not only is it correct, but it is verified. Let's do one more. Again, it's not too shabby, but it does involve a exponent, which is also going to involve a radical. So I want to make sure you can kind of see both. So if my original function is f of x, I'm going to go very quickly on those steps to find the inverse. Notice we do have a restriction here, and that restriction will follow us for the entirety of the question. So I'm going to switch my x and my y, and I'm going to start solving for y. So I know I need to add 2 to both sides. In order to undo a square, I take the square root. So the square root of x plus 2 is equal to y plus 4. So I know that the inverse is the square root of x plus 2 minus 4. This will be my red function. So we found it. Now we have to verify it. So we're going to verify by checking both compositions. So start with my f, which was x plus 4 squared. Ooh, I wrote too big. X plus 4 squared minus 2. And we're going to fill in that x value with what we think is the inverse. Square root of x plus 2 minus 4. So if I start simplifying this down, the negative 4's cancel because the negative 4 is not under a radical. So we treat it like a regular number. which means I'm left with the square root of x plus 2, quantity squared, minus 2. Well, the square root and the square cancel each other out, so I'm left with x plus 2 minus 2, which leaves me with just a plain old x, and that is exactly what we want to see. The opposite composition must also be true in order to verify. So start with the g function, and that is the square root of x plus 2, my square root a little longer, minus 4. So when we looked at the original was x plus 4 squared minus 2. These 2's cancel out, so I'm left with the square root of x plus 4 squared minus 4. Remember, squares and square roots cancel each other out, so I'm really left with x plus 4 minus 4, which comes out to x. Because both of them are coming out to x, now we are verified. So you have to be capable of not only finding the inverse, so understanding that x and y switch, solve for y, but you have to prove it algebraically. So that's composing the two, making sure that you get x's out of both because they're undoing each other. So I had an x and got a y, and I put the y back in, I should get the same x out, and that's what you're verifying.